Good morning. Welcome to our next episode in electricity. Today we'll be analyzing mixed circuits. Okay, just a bit of background. Just to let you know, this formula here, it is derived based upon Ohm's law and Kirchhoff's voltage and current laws. That's where this comes from. So no, you don't need to copy down the proof. This is more of a background story of why this formula is true. In fact, one way that I like to use as an analogy for resistors, you can think of them as traffic lights, right? So the time it takes for you to get back home is based upon how many traffic lights there are between, where you are, let's say at the mall versus where your home is. And the more traffic lights you go through, the longer it'll take for you to get home. And that's what's happening over here, okay? You start off over here and you want to travel all the way around to get to your destination. And the more lights there are, the longer it'll take. And that's why in your mind, you'll think mentally that, if there are 5 traffic lights over here, and let's say 6 traffic lights over there, and another 9 more traffic lights over there, if you add it up in total, there are 20 traffic lights. And that does work out mathematically with this. Okay, so that's one way of thinking of why this works out. But let's go through the logical reason as well. According to Kirchhoff's voltage law, the voltage around any sort of loop will net to a value of 0. So whatever you start off down here with 0, you'll gain through your source and you'll lose through your loads. So 0 volts will be equal to the gain through Vs minus the V through R1 minus the V through R2 minus the V through R3 and net to a value of 0. Effectively, what we want to do is we want to simplify the 3 resistors and make it as if it was one big resistor. Right, so when you went to the electronics store, you didn't go off purchasing 3 individual resistors. You just bought one because it behaved the same exact way. All right, so this formula here is completely correct. There's nothing wrong with it. But let's go and modify it so it starts to look like this formula here. According to George Ohm, he described that V is equal to I times R. So that's what we're going to do. We're going to sub in the value of I times R into each of these terms here. Another thing that I did was that I put V R of the source. Why did I call it VR? Well, I guess the equivalent resistance of the source. All right, I put it to the other side and just made everything positive, just to clean it up. All right. Again, V is equal to IR, so I made all the rest of them IR. Now, when you take a look at this loop over here, you'll see it's one complete circuit. There's no branches or breakaways or anything, all right? So whatever current you start off at the beginning, it's equal to the same current midway through. It's same as the current returning back to the source again. All right, so all the currents are exactly the same. So since I1 is equal to I2, which is equal to I3, which is also equal to the current leaving from the source, well, we could technically just divide everything by I. All right, so when we divide everything by I, we're left with this formula here. Okay, so that's where this formula comes from. VRT is equal to VR1 plus VR2 plus, sorry, RT is equal to R1 plus R2 plus R3, so on and so forth. That's the origins of it. Any questions before I move on to why resistors in parallel looks like that crazy formula? Okay, as this one here is probably the most self-explanatory of them of all. If you treat each one as a traffic light, you have to add up the total amount of traffic lights to figure out how much of a delay it takes to go back home. You can think of resistance as the opposition towards current flow. Now, my analogy is not perfect because, again, I said it takes longer to get back home, but in truth, with regards to these circuits over here, the time for the electricity to pass through the circuit is the speed of light. Right? The electrons don't travel the speed of light, but the energy does. So what takes longer? The rate of current flow. That's what takes longer. Okay, so the speed of the energy is still 3 times 10 to the 8 meters per second, no matter how high or how low the resistance. It's just the quantity of electrons that return back home does decrease with a higher resistance. Okay, so next is resistors in parallel. Back in grade 9, you would have seen this formula over here. Probably just nodded your head and let it be. And that's perfectly fine because you haven't covered Kirchhoff's current law and Kirchhoff's voltage law to properly describe what's happening here. Okay, so again, this is an example of where the resistors are in parallel with each other. And yes, they will be parallel with the power source. Okay, so in other words, if you didn't know what was inside this big box over here, you're trying to look for the total equivalent resistance at the end of the day. Another thing to keep in mind is that the circuit up above This is just a way to make it look visually appealing. All right. Whenever you draw an electronic circuit, you avoid drawing diagonals. They can't be avoided 100% of the time, but they can be avoided, 99% of the time. So if you can, avoid all those diagonals because it makes it an ugly picture and harder to follow. So grammatically speaking, the top diagram is the correct diagram, but in your head, treat it exactly the same as the diagram down below. All right. So the current that's leaving from this power source over here, it is divvying itself amongst all the three resistors, just like in this diagram over here. Does it have to divide it equally? No. Can it? In theory, yeah, it's possible. If all three resistors had the same resistance, then yeah, as a good parent, you're going to divide out, all the food to all your children equally, right? If they're all equals. Okay. So now let's try to talk about why this formula here is true. All right. I mean, we're going to start off with Kirchhoff's current law. The current that's going into all the resistors is equal to how they're divvied up amongst all the resistors. Okay, so current of all the resistors in parallel, if you're wondering what the letter P is equal to the current going through R1 plus R2 plus R3. Next, we're going to pull out Ohm's law. V equals IR and isolate for I. So I is equal to V divided by R. And again, sub all of that into there. I know it looks like a big mess right now, but one of the rules about resist or any components connected together in parallel is that they'll all share the same voltage. So the voltage of the source, let's say from your house, is at 120 volts AC. Then the voltage going to your TV set is 120 volts AC. The voltage going into your stereo system is also 120 volts AC. And the voltage going through, your gaming system, whatever it may be, was also 120 volts because they're all connected together in parallel. All right, so VP is equal to V1, which is equal to V2, which is equal to V3. In other words, we can just divide it out. And that's how we derive out this formula here. Okay, so this is the story of resistors in parallel. And yeah, if you only had two resistors, just drop out that third term. If you had a fourth resistor, I hope you can see this pattern that we have here. All right, so R4 would look like that, and R5 would look like that if you were to wire it up. Any questions so far? Okay, again, this is just the backstory of where this formula came from. And we're just going to cut to the chase when we start doing our homework questions. We're going to use the resistors in series formula, and we're going to use the resistors in parallel formula in solving today's homework. No, you do not need to show the proof. I just wanted to share that it does exist. Another thing that I want to share with you that does exist as well is something that you might learn of in electronics class, because some of you guys have taken that class first. All right. And your electronics teacher would have shown you this formula up here and say, hey, use this and it works. It does work. All right. And if you decide to use it, I'm okay with it, but I'm not a big fan of it because what it does is that it does a big shortcut and you miss out on the story in between. There is an A equal in the middle picture. No, because again, this is A of, I don't know, the source, A1, A2, A3 as in amperes. All right. I suppose I should have used the letter I. So IS is equal to I1, I2, I3. Hopefully that answers your question there. Okay. Now for this picture, I guess I forgot to mention it. The reason why I drew a circle and wrote the letter A is to describe that there's an ammeter there. Okay. So there's an ammeter placed right at the beginning. And what we're trying to get at is that the ammeter at the beginning is equal to the readings of the ammeter through each of the resistors all added up together. That's all it is. Okay. So why is this formula bad? Well, first off, let's talk about why does the formula work in the first place. All right. There's origins for everything. Okay. So we start off with this formula here because remember, this is the shortcut answer for this formula here. So let's go off and derive that formula. First off, in order to add fractions, you need to have the same denominator. And the easiest way to guarantee that you have the same denominator is that you multiply the denominator from one side to the numerator and denominator of the opposite end. In other words, 1 over RP is equal to R1 all over R1 times R2. And then we're going to rinse and repeat on the other side as well. All right, so we're going to multiply R2 into the numerator and denominator of the second resistor. So it'll look something like that. And now that they both share the same denominator, now you can add the two numerators. Lastly, you need to isolate for RP, and you could do it the long way, where you multiply both sides by RP, you multiply both sides by R1 times R2, and then you divide both sides by 1, and you divide both sides by R1 plus R2. But that's 4 steps, and that takes a long time, all right? The fastest way to get to the answer is to simply reciprocate. So as long as you have a fraction on the left side and a fraction on the right-hand side, you can quickly just do a quick swap-a-rooney of the numerator and denominator, like so, and you will get to the same exact answer. Okay, so the reciprocal of 1 over RP is RP, and the reciprocal of that mess turns out to that. And that's how this formula is derived. So if you do want to use this formula in the future, it doesn't bother me. I'm fine with it. But I don't want people to assume that this is the best formula out there, because this is the problem about assumptions. This is true for 2 resistors. Does that mean that if you have 3 resistors, just by looking at the pattern, should that be the correct answer? Okay, I want you to think about that. Is this the correct answer? All right. If you go through it quickly in your mind, it logically makes sense and you think it's the correct answer, yet it won't work out. Okay. It is not the correct answer. So to prove to you that's not the correct answer, let's go off and derive the proper formula, and then you can compare and contrast. So this time around, we're going to start off with 3 resistors in parallel. Again, the only way that you can add all these 3 terms together is if they share the same denominator. So in other words, R1 needs to be multiplied by R2 and R3, and we need to do R2 and R3 in the numerator, like so. And yes, we're going to rinse and repeat for all the other terms. So you're going to get a big, crazy looking thing that looks like this. Okay, 1 over RP is equal to R2 over 3, same common denominator, plus R1, R3, same common denominator, R1, R2 over the same common denominator. Now you can add all the numerators together. And if you reciprocate it, this is the correct formula. And you can see that these two do not match up in pattern. And that's why I don't recommend using this formula up here. It works well with 2 resistors in parallel, but once you have 3 resistors, well, then you end up having to do this crazy thing in solving it, and that takes a long time. All right. The fastest way of solving any of these problems is by using the shortcut. If you know that the reciprocal of both sides will get you to the correct answer, why not just do that instead? All right. So if you're trying to solve for your resistors in parallel for 3 of them, why not just do 1 over R1 plus 1 over R2 plus 1 over R3 to the power of -1? That's a much faster way of getting to your right answer. Okay, try it on your calculator. It's very quick to type out. Same as this formula here. It's not much more difficult than the one taught in electronics class. All right, so RP is equal to 1 over R2 plus 1 over R1 to the power of -1. Okay, it's very quick to type out on your calculator. Optionally, you can write it out like that as well. That does work out. Okay, and to describe why this is true, you know what? I'll just describe right here in the middle. Okay, why is 1 over RP equal to 1 over R1 plus 1 over R2 plus 1 over R3 to the -1? Again, the -1 means to take that value and do 1 divided by. So we're going to do 1 divided by 1 over RP, which effectively is 1 multiplied by the reciprocal, which is RP over 1, which gives us RP on the left-hand side. On the right-hand side, we're going to do the same thing, but out of sheer laziness, why don't I just say 1 all divided by everything inside the brackets, 1 over R1 plus 1 over R2 plus 1 over R3. And that's all you're effectively doing in your calculator. You're doing 1 divided by, and then here comes the open bracket. The open bracket is for all the mess downstairs. Okay, so you could use this technique down here in solving your problem as well. It will get you to the correct answer. And it's much faster than using the method up above. Okay, again, none of this needs to be copied. If you really want this reference here, you can find it again in the video recording if you rewind back, or open up this PowerPoint slide at your own leisure. Okay, now let's get to the grunt of the lesson. I'll start off with this example over here. And yeah, I'll give you guys a minute to work away through it. Here comes countdown timer. I'm not going to give the full 5 minutes. I'm going to give 1 minute. Okay, hope that gives you guys enough time towards jotting this down. And let's start solving this problem. What we're trying to do is that we're trying to take this big equation here and then drop it down so it's represented by one big fat resistor. Okay. Now, if you visually look at this, you can kind of see that there are brackets here. Effectively, we're doing the same thing as bed mass. All right. So you're going to deal with brackets first, and then everything inside. Well, yeah, everything's inside the brackets first, and then we work out from there. And the most basic thing in there are the additions. All right. So we're going to first add the 4 ohm with the 2 ohm resistor together first. We'll take care of this first, and then we'll deal with the 2 resistors that are in parallel. So with resistors in series, we know that all we need to do is just simply add. So 4 ohms plus 2 ohms will give us 6 ohms. Now this entire picture can be simplified down. Okay, so instead of drawing these 2 separate resistors here, we're going to represent it by one bigger resistor. And just for clarity's sake, I'm going to go and label all of the resistors here. Okay, so most of the resistors haven't changed. The only thing that has changed is whatever that's in red. All right, the 4 ohm plus 2 ohms will give you 6 ohms. If you're wondering how must you show your work over here, well, really, as long as you just break it down and you show me like in the next logical stage, that's fine. All right, and what you would do to add it up. As for the formalities of showing formulas, you could cut corners and just cut to the chase of telling me what you're going to do. So 4 ohms plus 2 ohms will give you 6 ohms, and that's why this resistor over here has a resistance of 6 ohms. All right, and as I mentioned earlier, you want to deal with the most inner bracket first. So you'll see that there's these 2 separate inner brackets. Okay, I'm going to deal with the inner bracket on top separately than the bracket down below. I'll start off with the one on top. Okay, you can see that the 6 ohm and the 8 ohm are parallel with each other. And as they're parallel with each other, then you have to use the formula of 1 over Rp is equal to 1 over R1 plus 1 over R2. In other words, 1 over 8 plus 1 over 6 is equal to 1 over Rp. Now, to save some time, as I said, the fastest way to get to your answer is to reciprocate. And the reciprocal of 1 over Rp is Rp. And the reciprocal of this, well, let's pull out our calculators and see what it is. All right, so open bracket 1 over 8 plus 1 over 6, close bracket to the power of -1. On this calculator, I do have that shortcut button, x to the -1. Alternatively, you can do x to the power of -1 close bracket if you want to. They'll both get you to the same correct answer of 3.42857. Do you need to carry that many significant figures? You can probably get away with 3.43, right? You know, I'm just going to leave it at 3.429. That's more than enough to get to our final answer. Because if you look at our givens in this example here, I know it's crude, it only shows 1 sig fig. That means your final answer, you're only certain to 1 sig fig as well. Okay, now you don't have to just do one piece at a time when you're solving for these problems. You could take other parts as well. For example, if I want to deal with this guy over here, yeah, I could do that calculation in unison. In fact, I'll just do it in a different color so that you can see where I'm getting my calculations from. So 1 over RP is equal to 1 over R1 plus 1 over R2. If you really want to name it as R3 and R4, that's up to you. I'll just reset the clock every time. Okay, so 1 over 4 ohms plus 1 over 6 ohms. I forgot my omegas. Let me just add them in. There you go. In fact, I like to reciprocate at the beginning just to save myself that one step here. RP is equal to this to the -1. And now I'm just going to show you a different way of getting to the correct answer. As I said, to the power of -1 means you're going to take the answer and you're going to do 1 divided by it. So here's the easiest way to type in your calculator without hitting any of the special black buttons. Okay, well, except for brackets. Okay, I'm going to start off with the number 1, and I'm going to divide by. In fact, I'll just tell you logically what I'm doing. I'm doing 1 over 4 plus 1 over 6. That's all I'm doing, right? To the -1 means take it and reciprocate it. So here's my calculator. 1 divided by, open bracket, everything downstairs. 1 over 4 plus 1 over 6. And yeah, you could probably hit the fraction button on your calculator and it'll give you the same results. Because once I hit equals, I'll get the same answer no matter which way I decide to solve this problem. Now, one thing just to mention about, because I forgot to talk about this earlier, the whole analogy of traffic lights. You'll notice that if you connect them together in series, yeah, it's going to take you forever to get to your destination. That's why your resistance increases. All right. But if you place them in parallel, it's kind of like you having more roads in a street. So if they add more lanes to that street, you know that traffic will flow better. And that's what's happening, for example, in this lower example over here. Okay, now we have 2 separate traffic lanes. We have one traffic lane where there are 6 traffic lights, and we have another lane which have 4 traffic lights. Okay, and the moment that you have more lanes, you know you're going to get home sooner because there's less impedance that's holding you back, or there's less resistance holding you back. So the value should decrease. You should get home a lot sooner. In other words, your final answer with any resistors in parallel will always be an answer less than your givens. So you can see that the 2.4 ohms is less than your 4 ohms, and it's also less than your 6 ohms. That is always true. Okay, so that's a good way to check your answers. Your resistors in parallel will always have an answer less than your smallest resistance. In fact, if the 2 values were identical, traffic improves by double. And I hope that makes sense. All right. So if one has 10 traffic lights and your lower one has 10 traffic lights, it's the equivalent of having just 5 traffic lights because you're allowing more cars to travel at once. So you get home sooner. Okay, most of this has already been animated out, so there's the animated answer. Now let's clean up this diagram here. Okay, since we have the 6 ohms and 8 ohms all represented by one resistor, and the 6 and 4 represented by yet another resistor, we'll just redraw the diagram again, all cleaned up. We can still visualize that there's big brackets on the outside. But before we deal with the brackets on the outside, we need to deal with the resistors in series first. So that's what we're going to do. We're going to add the 8 with the 3, which will give us 11 ohms, or 11 and change. 6 plus 2.4 will give us 8.4. And here's our next diagram. We'll rinse and repeat one more time. 1 over RT is equal to 1 over R1 plus 1 over R2. So 1 over 11.4286 ohms plus 1 over 8.4 ohms. We're going to bring that to the -1, 1 over RT. And yeah, I'll show you the other button. Why not? Okay. So open bracket, 1 fraction, 11.4286 plus 1 fraction of 8.4, close bracket, to the power of -1. It's just yet another way to get to the same answer of 4.84. And that will be our answer here. Okay. So our RT will be equal to 4.84 ohms no matter which way you decide to solve this problem here.